There we go. There you are, sorry.
Thank you. Now, if everyone can see my desktop, I've entered into our GitHub page, which I'm going to put a link to in the chat. And I would like everyone to follow this link. I'm just going to take a second or two just to let everyone click on this link. And once you have gotten to this GitHub page, you're going to see a big green button that says code. And I would like you to click on this button and then go to download zip. Click on that. And you should automatically begin downloading the folder. It's a small folder, so it shouldn't take too long. Just going to close this. And now, once you've downloaded the folder, I would like you to just drag and drop it into somewhere easy to find on your computer. I'm just going to do it on my desktop so that it's very easy for me to find. Then I'm going to open up the file. And now I will have all of the content I'm going to need to complete this workshop, such as the R Workshop RMD file that we're going to be working through later, and also the answers files and a copy of the slides that you can also go through as well. Right, so I'm hoping that everyone was able to do that all right and were able to follow along with me. Yeah. And with that, I'm going to jump back into reviewing the slides. All right. So the first thing I want to talk about today is why we have chosen to do this workshop. And one of the reasons is that, well, biomedical researchers and graduate students, like many of you probably are, they tend to come from a diverse variety of different backgrounds. And not all of these backgrounds include a lot of training in computational tools such as Python and R. Furthermore, getting more experience with these kind of tools can be very difficult because many of the courses provided at UBC, they could maybe provide a better background in statistics, such as Stats 540 or 445. These courses assume a working knowledge of R, or they have a very steep learning curve for those unfamiliar with it. Now, this makes me really sad because coding with programs like R is really useful for publishing your analyses because it makes your analyses computationally reproducible. This means that rather than a collaborator or a future researcher needing to follow your exact guidelines for doing something in, let's say, Prism or Excel, they can just load up an R script and run it with a push of a button quickly and easily. And this means that you can make your work easily reproducible by publishing your R code along with your manuscripts. All right, so during this workshop, some of the main points we're going to cover include getting oriented with the layout of our studio, which is where we are going to be doing most of our work with R, getting familiar with some of the basics of coding in R, such as packages and functions, getting familiar with some of the basics of working with data frames in R, which is how we traditionally store data. Then we're going to cover an introduction to plotting in R using a package called ggplot2. And finally, we will end things with a very, very brief description on how to do some basic statistics in R, such as the t-test. All right, so here are the learning goals for the lecture. I'm not going to read through all of them piece by piece, but I encourage you to review them later on if you're looking back over the materials of this lecture. But with that, I'm going to move on to actually talking a little bit about R. So what exactly is R? Well, R is both a coding language and a software environment that can work across multiple different platforms, such as Windows and Mac OS X. And we use R mostly for statistical computing and graphics. Another important point about R is that it is an open source environment, which essentially just means that nothing is hidden behind copyrights or licensing. Anyone can use R, and if you get really good at it, anyone is allowed to actually contribute to R. Finally, and probably the most important factor for all of you, R is an extremely popular tool for biological statistical analysis for reasons that I'm just about to overview. So why would we use R rather than some other programming language? Well, for one thing, it is free. Pretty obvious example right there. Another important thing is that R is really good at making graphics. I personally think R has the best graphical capabilities of any coding language I have worked with, and I highly recommend it for this task. Finally, and perhaps most importantly, R has an incredible variety of packages, especially statistical packages and biological analysis packages. We're going to talk a lot about packages later, but for now, just think of them like a collection of programs that can be run in R to complete a specific set of tasks. There is an R package for basically every analysis you can think of. I cannot tell you how many times I've been completing a project in some other language like Python and have then had to integrate R into my work, like just add an extra script into the pipeline, just because R was the only language that had the package I needed. Now, I also want to take a second to describe some of the cons of R, of which there really aren't too many. For one thing, in certain very specific situations, languages such as Python and MATLAB can be a bit faster than R, though this change is usually very small. Another flaw is that R uses unique syntax. And what this really means is that if you learn R, it is not going to help you so much when you're trying to learn different languages, such as Python and MATLAB. It can be very hard to switch between languages. And then finally, R does have a problem with there being almost slightly too many packages. And what I mean by this is that since R is open source, it is easy to publish R packages, and people have published a lot of them. So there are some packages that are redundant or poor quality. You might run into these as you're working with R, and you just want to try and stick to very popular packages that have been tested and published officially. Now, everything I just went over were pros and cons that are kind of generally accepted in the greater coding community, but I also want to quickly tell you about my personal experience with R as a bio student who has been working with it for a few years now. And that is that I think R is a great language for statistical analysis and graphics and whatnot, but I find it is not the best when trying to create programs and pipelines. What I mean by this is that when I had some big multi-step computational data analysis pipeline that is using separate programs and is interacting with my operating systems, I find R struggles a bit, and I prefer Python. I'm sure that there are some people out there who would disagree with me on this, but that is just my personal experience that R is best for specific statistical analyses. Okay, with that kind of background out of the way, let's launch into how we actually use R. First things first, I want to go over the difference between R and RStudio, which I believe is a major source of confusion for newcomers. R is a coding language. It is what actually runs the code, and it is not user-friendly. RStudio is what we call an integrated development environment, which helps you create the code and is user-friendly. So we're going to be doing all of our work in RStudio, and we will not be touching R directly. Now, I think this can be confusing for some people, so I'm going to explain it one more time using an analogy. We can think of R like the engine of a car. It is what is actually doing all the hard work, but when we want to drive a car, we do not flip up the lid, like grab the engine and then work with the engine from there. When we want to drive, we use all the controls on the dashboard. And the dashboard is going to be our equivalent of RStudio. So we're going to work the engine using the dashboard. I hope that helped someone. All right, now let's get familiar with RStudio. RStudio is split up into 4 main sections. a scripts section on the upper left, a console section on the lower left, then an upper right-hand portion that includes the environment tab, and a lower right portion which has a variety of different tabs. Now let's go through each of these in more detail so you know what each of them are for. Okay, so the most important section of our studio is the scripts section. This is where we're going to be creating our R scripts. R scripts are essentially where you can write down all of the commands you want to use, along with some helpful comments, and then run all of those commands in R. This is extremely useful because it means you write down everything you are doing in your analysis. You can then repeat that analysis with the push of a button. This is why we're going to be doing 99% of our work within this scripting section. The next section we need to mention is the console section. This is the one on the lower left. This is the portion of RStudio that shows you what is actually being run in R. So this is looking at the engine. You can run code directly in the console by typing into it and hitting enter, but we will be typing our commands into R scripts pretty much all of the time. The only other important thing about the console section is that it is where the output of your code is going to be displayed. So for example, if you type 2 + 2 into a script and then run that script, the number 4 is going to be outputted down here in the console. And we're going to see several examples of that once we actually open up RStudio. All right, now we have the upper right-hand section, and this includes the environment panel. This is the most important panel here. It gives you an easy access to all of the objects and data sets you create and download. We are going to be looking at this panel a lot. Then there is the history panel, which contains a record of everything you have already run in R. You would think that this would be really important, but since we are going to be writing most of our code down in our scripts, I actually don't use this too much because I can already see all the commands I've run. Finally, we have the connections panel, which can be used to connect with databases through RStudio. I have never actually used the connection panel, and we're not really going to be covering it much today. It only comes in handy if you're connecting to a very specific set of databases. Finally, we have the lower right-hand section where there are several useful tabs. We have the Files panel, which lets you browse through and open, /delete, /rename files. This is useful sometimes, but generally I find it preferable to just move files around using your system's built-in file manager, like Finder for Mac users. So we're not going to use this maybe as much as you think. Then there is the plots panel, and this is where the plots and figures you make in R are going to be outputted. And then there's the package panel, which lets you see all the different R packages you have installed and loaded, which can be a useful overview, but I rarely find myself looking at it. Then there is the help panel, which lets you look at help files for different functions. This is very important, and we will discuss it more later. Then finally, we have the viewer panel, which is only used for very special kinds of visualizations. I've only used it a couple times, so it's not really going to be very important for us today. All right. So now that we know the basics of RStudio and kind of how it's organized, I want to take a moment to talk to you about how we're going to control our workflow using R projects. R projects are essentially just these special directories / folders that we create, which contain our project files. And I want you to think of these like little boxes you're going to build that contains everything you will need for your project, such as all the scripts and data tables and etc., all in one nice, neat little package. Now, there are a few reasons we want to use R projects. The first is that R projects make it easy for us to define our working directory. Now, what is a working directory? Well, a working directory is basically a folder where R is going to look for things. For example, if you ask R to load up a data table, it is going to look for that table in your working directory. So it's not going to search anywhere else on your computer at first. It's going to just do the working directory. So if we define this clearly, we make it easy to organize everything for our analysis. The second reason is that it preserves the command history for our project, which can help us keep things organized. And finally, our projects are what we use to integrate version control into our studio. Now, version control is beyond the scope of this tutorial, but it is extremely helpful, and it is the main reason I recommend getting used to our projects now so that it is easier to do version control later. I'm really hoping we can get to version control in a later version of this tutorial, a new tutorial at some point, but that's for another day. All right, so this slide details how to create a new R project. We're actually going to do something a little bit different from this. And that is we're going to turn the directory you downloaded from GitHub into a project directory. And I'm actually going to walk you through that right now. So I want you all to open up RStudio while I'm busy changing the screen sharing. And then we are going to make our first R project. All right, so one thing I'm quickly going to mention, because I noticed some new people are here, we're just about to launch into using R. So please go to the GitHub page and download a zip of the material if you have come in late, because we're going to need it for this next step. All right. So I'm hoping now that all of you are looking at a screen that looks something like this. And what I want you to do is I want you to go up to File, and then go to New Project. Okay, from here, I would like you to click on Existing Directory. Wait 1 second. Thank you, Megan, for answering that question. Yes, please go to Existing Directory. I'm going to click here. And that's going to bring up a little screen like this. Then I would suggest hitting Browse. And I want you to find wherever you have put your the workshop folder on your computer. For example, I know I put mine in Desktop. So I'm going to click on Desktop. I'm going to find this BCCHRI yada, yada, yada 2022 folder. I'm going to click on it. Then I'm going to hit open. And I'm just kind of going to just pause. I'm just going to sit here for about a minute in case anyone has any problems with that or anyone wants to ask a question here. All right, I think that's enough time. I'm hopeful that all of you were able to find wherever you, hope you all put your folder in a good place and were able to find it. So now I'm going to just hit Create Project, as it already knows what I'm looking for. Then RStudio is going to reload. And now you'll see that if we look at our Files folder, we can actually see the all the files that you guys downloaded. And now whenever we ask R to do something, it's going to look through this directory for what we want to load up into R. Now with that, we're actually going to switch now to mostly working in RStudio for this tutorial. So I'd like you all to click on this rworkshop.rmd file that you should be able to see now within this Files panel. And after you do that, you should be seeing something that looks just like this in our little script section. I'm actually going to make this a little bigger. And before I start going through this script, I want to answer a question, which is what did we just open up? What is an RMD file? Well, an RMD file, the script that you currently have loaded up, is a very special kind of R script called an R Markdown file. Now, R Markdown is a powerful tool for integrating R code into documents and websites. It's actually very useful for creating publications. But for now, we are just using it because it's a very convenient scripting format when constructing tutorials such as this one. So in our Markdown files, there are two types of input. Everything in this white area here is part of the Markdown section of the Markdown file. And this means it is just plain text that cannot be run in R. We can then create a coding section using 3 grave accents, which is this sort of thing, little thing up here in the upper left corner of your keyboard. It's right underneath the escape key. And we're going to follow that up with squiggly brackets and then R. So I've already done that here. And now everything in this gray box is a code chunk. And this can actually be run by the R coding language. And if we want to put any notes into these coding blocks, we need to turn them into comments by starting the line with a little hashtag symbol. So you'll notice that all of this text is green, and that's because it has a little hashtag symbol in front of it. This will let R know that it's going to ignore everything in this line, which is important because R won't know what to do with text. It'll just throw an error if it tries to run that. So now let's actually run something by hitting the green arrow at the top of the block. So you can see this little arrow here. I'm going to hit it. And boom, it calculated 2 plus 2. And you can see that both in the output window below, and we can also see this down in the console window. Now, hitting this green arrow, there's one problem with it, which is that it runs everything in the block all at once. And sometimes we want to run things line by line. In fact, most of the time, we want to run things line by line. And if we want to run just one line of code, we can do it by selecting that line, like just going to it, and then hitting Command plus Return if you're on a Mac, or Control plus Enter if you're on Windows and Linux. So now we're going to basically do our first, like the simplest question I can think of, which is I just want you to run this 3 plus 6 command and none of these other commands using Command plus Enter or Control plus Enter. So I'll do that now. And you can see that I've only outputted 9 and not the results of these other calculations. And this is how we are usually going to run the code in our blocks. So as we're going through the rest of this tutorial, I'd like you to try and run it using these Command plus Enter or Control Enter shortcuts. Okay, there's all the boring stuff out of the way. So let's get into how to do things that are a little bit more interesting. So the first thing I want to do is I want to introduce you or reintroduce you to packages in R. So R has many useful built-in tools, but the true beauty of R is in its open source packages. There is an R package for basically every problem you can imagine. You just need to figure out what the package is called and how it works. Today, we will be working with the Tidyverse suite of packages. Tidyverse is a large set of packages that are all related to data analysis and all share a common data organization philosophy so that they all are able to work in harmony together. As an example, the ggplot2 package that we will be using later is part of Tidyverse. You can find more information on all the contents at their website, which I've left a link in the Markdown file, but I'm going to move on now. So when we want to use a package like Tidyverse, there are a couple of steps we need to complete. First, you need to install the Tidyverse package by running install.packages tidyverse down in the console. And hopefully you've all already done this as was described in the email, but if not, that's actually okay. You can just copy this now, copy it into the terminal, hit enter, and it should start the downloading process. And know that once you've done this though, once you've run installer packages, once you've done this a single time, Tidyverse will be on your computer forever, and we don't have to rerun this at all. So the second step you need to do is you need to load that package into your R session using the library command. And so I'm going to do that right now. I have library tidyverse here, and I'm going to hit this little arrow in order to load it up. And this you actually have to run every time you open up RStudio. So whenever you open up RStudio, it will become unloaded and you have to load it again. That's why we usually put library right at the top of whatever script we're working on. All right, so now that that's there, we're going to have all the tools we need for everything that comes next. So now I want to take a second to talk about variables. Whenever we calculate or create something in R, we can save what we made as a variable which can be used later. And we do this by specifying a variable name and then setting it as equal to something else. This can be done either using an equal sign or an arrow. I personally prefer the equal sign because it is much faster to type. It really makes a big difference once you start doing a lot of coding. So we're going to stick to that today. So assigning a variable with an equal sign, we can run this command return. You can see that after we do, in our little environment, a new thing has popped up where we can see X, and we can see that it is equal to 4. This is why the environment tab is so important. It lets us look at everything we are loading up into R. Now, once we have saved the output of 2 plus 2 in a variable called X, we can then use that variable in further equations. For example, now I can write 10 plus X, command enter, and now I get the number 14 as an output. Obviously, this is super simple, but I hope you can imagine how once you start getting really complex chunks of code, this becomes very important to be able to define variables and to be able to give them descriptive names, etc. So now I'm going to move on to vectors. Vectors are one of the most simple and common ways that we store data in R. There are a couple different definitions of the word vector in like different fields like math, but for our purposes today, a vector is basically just a list of things, such as numbers. It's just a list. So we're going to create a vector and store it in a variable using the C command. So I have a little variable that I've named vec, and I'm making it equal to this list of numbers, command enter. You can see again up in our environments panel, we now have a new vector that has all of these numbers in a little list. And once we have created our vector, we can then select values from a vector using square brackets. And this will select the very first value in the vector. And then I could change this to vec5. That will select the 5th vector, so on and so forth. All right, so that was all still pretty simple and pretty boring. So now I want to move on to something a little bit more interesting with functions. So we can use functions to complete a variety of tasks in R. And these tasks can range from simple things like calculating means to performing these really incredibly complicated computational analyses. Some of these functions are built directly into R, but the most useful functions are only available through packages such as Tidyverse. So let's use some of the really most basic functions to calculate the mean and standard deviation of that small vector we made up here. So rather than typing out a whole equation, we just put mean brackets vec, and we immediately get the mean of all the numbers in our vector. You can see it's 4. And then we can do the same thing by putting SD for standard deviation, looking at that. And we immediately get the standard deviation of our vector, which is about 2.16. Now, there are a lot of different functions in R, but the single most important function in R is going to be the help function. This function can be used to get information on any of the other functions in R. So I would like you to try running help on the mean function we used earlier. And when we do this, a small window is going to pop up on the lower right. So we do this, and we can see this window pops up. Now, looking through this, something you might notice is that even for a really simple function like mean, there's still a lot of information here. But the most important sections, and the sections I'm always focusing on, are usage and arguments. Usage is going to show you what the function is going to look like when you type it into a script. And it also shows you what the default values are for each argument. And now, what is an argument? Well, this argument section explains what all of the different arguments we're going to input into our function are, and it explains what they do, and it explains what they accept as inputs. Now, this is probably a good time to explain the different ways you can specify arguments when you're using means. So in order to do that, we're going to create another vector real quick. And we can see here it's a bit longer, and you'll notice that there is an NA in the center of this vector. Now, what NA means in R is that there's something missing in our vector. There's basically just a hole in the center. And if we want to calculate the mean of our vector, we're going to need to remove this NA. So we're going to use some of the extra arguments for mean to trim off 10% of the observations and remove this NA value. And to do this, we have two options. We can either put all of the inputs directly into the function in order. So as an example here, I'm going to do mean, then my vector is going to be Rx. For trim, I'm going to set it to 0.1. That's going to trim off 10% of the values of a vector from either side. And then for na.rm, I'm going to set that to true, which means that the function will ignore na values. So run this here. Run the vector first, and then I will run this here. And we see that even though we had an NA, we were still able to calculate the mean of our vector, which is about 4.42. Now that's one way we can specify the arguments. The other way is that we can specifically call using the name of the argument. And when we do this, we can do things in any order we want. So here, rather than just putting them in, I say x is equal to the vector, the trim is equal to 0.1, and na.rm is equal to true. And when we run this, we will get the same output. Even if we switch things around, we will still get the correct output. So this is the way I prefer to specify arguments when I'm using functions, mostly because as functions get more complicated and they get more arguments, doing things in order becomes really tedious and hard to keep track of. So I would recommend, we're going to try and stick to this for most of this tutorial. Now we're going to move on to our first kind of real question. And let me just, so let me see something here. That's strange. Oh, well, this is embarrassing. It looks like the answer to this question is still here. Is that for all of them or just for? Yes. Well, that's embarrassing, but nothing I can do now. So I'm going to embarrassingly ask you to delete this answer, as I don't really have any other options now. I'm sorry, everyone. I must have made a mistake when uploading this to GitHub. But before we get into this question, I would like to ask if anyone has any questions on this, as this is the first kind of complicated thing we've done so far today. And maybe while people are thinking about questions, you can just scroll down to all the other questions and just delete the answers that I left in there. Hopefully none of you have photographic memories. Okay. Actually, it looks like I didn't put in all the answers, which I'm proud of. Okay, that's good. I was only questions 1 and 2. Okay, but yes, so.
Keegan, I got a question for you.
Okay.
When you said the orders can get mixed up, or you can mix them up and they'll still give you the right answer, your vector, though, does it always have to come first? X.
Nope.
It can be any. Oh, perfect. Oh, that's really nice.
Okay, but I do want to say one thing, just because you brought that up, which is that we prefer to do them in order, even though we're specifying the name. Like the real use of this is when you want to skip something. Like let's say I just wanted to put X and NA.RM and I didn't want to trim anything. It's useful that I can just put, I'll actually do the example. I can just put X equals vec2 and then NA.RM equals true. It's really useful that I can do that and I don't have to say anything for trim. We don't like it when people move around orders for no reason. It just makes things really confusing. We get very used to the order. So yes, you can do it any order you like, but we try and stick to the order it shows. Okay, but with that question answered, I'm just going to give you guys about 5 minutes to complete this first question. What I want you to do here is I want you to use the help command to look up how the quantile function works. And after reading this, I would like you to please calculate the quantiles of a vec2 vector using one of the continuous sample quantile types. So I'm going to have you use the help function on this quantile function. It is just named quantile. And then I would like you to use this function. So I'm just going to turn off my camera for a second and give you guys, I think maybe just 4 minutes would probably be enough. This is a fairly easier question.
If you guys get stuck at any point, feel free to just speak up or put it in the chat. I can help you out, no problem.
All right, 4 minutes have passed. I'm hoping that all of you had a chance to complete the question, but if not, we are about to go into the answers now, so no worries. So I'm just going to copy the answer in from our answers file. You can see that the first thing we needed to do was just look up help quantile. And after we do that, we get all of this information, but reading through the question, we should know that one thing we need to know is just x, which we wanted to make our vec2, na.rm, which we want to set to true, and then type, which after reading that this is a number which selects one of many different algorithms, we can just look down into the details, which goes over the types, and reading through, we can find that all of the numbers from 4 to 9 all represent continuous sample quantile types. So really any number that, if as long as you chose a number between 4 and 9, I would consider this question correct. And when we do this, we can calculate the quantiles for our vector. Right. Hopefully no one had any problems with that. And we're now going to move on to talking about how you can create your own functions. So creating your own functions is at the most basic level pretty easy. You just have to use the following format where you create a variable name for your function, and you set this as equal to the function command, then the arguments go in here, and then all of the inner workings go between these two squiggly brackets. Now, creating your own function can allow you to create powerful tools that are specialized for your analysis workflow. However, creating meaningful functions requires an understanding a variety of other coding principles, for example, for loops and if-else statements, etc., etc. And these are all beyond the scope of this workshop. We hope to come back to the topic of making functions in future workshops, but for now, we're just going to move on. All right, so now I want to talk about data frames. Vectors, what we've been working with, are a very simple way of storing data, but they are also very limited. Most of the time, we are going to be working with data that is stored in R data frames. And these data frames are essentially just tables similar to the ones you might make in Microsoft Excel. So to look at an example of this, I'm going to create the simplest data frame possible by running this command here. And we're going to take a look at it using the print command. So print data. And we can see here we have a super basic data frame. We have two guys, Sam and Mike, and then we have their heights over here. And once we have these data frames, we can select specific columns from it to look at specific parts of the data. For example, I am going to select the height column by using the name of our data frame, then this kind of money $ symbol, and then height CM for this column. And then we get the two height outputs. We can also select a row from the data frame using data frame, then square brackets, row number, comma. So I'm going to select the first row of our data frame here. So now I am just looking at Sam and his height. This will become more useful later on, so you may have to refer back to this. But now we're going to move on to look at a slightly more complicated table that has some actual relevance to biology. So we are going to load up this sleep DF data frame. Now, hopefully everyone will just be able to load this up easily as we have defined our working directory correctly. And then we're going to look at this data in a separate tab. So I'm going to run this, and this is actually going to open up another tab. We can look at this data. You can see that we have the names of a whole bunch of species, then their feeding behaviors, the order they belong to, conservation status, sleep total in hours, REM sleep in hours, and then brain and body weight in kilograms. Okay, and we can move back to our workshop by clicking on its little tab up here. And now let's get to working with this slightly more serious data frame. So first we want to look at subsetting, because for any decently complex data frame, we are inevitably going to want to subset it. We may wish to extract only the columns that are important for our analysis, or we may wish to look at data that meets certain criteria. There are multiple ways to complete both tasks, but today we will be doing everything using R's built-in subset function, which is my preferred way to subset data. So this function, subset, it can be used to subset our table in two different ways. The first is using its select argument, where using the select argument, we grab specific columns from the data frame. So you can see here I have subset of sleep-DF, and I am selecting the name, feeding behavior, and body weight columns. Oh, do we have a question?
We have one. I had this issue before too, so I remember this. View, I believe the V needs to be capitalized. If you're having issues with it, try that and let me know if that works.
Mm-hmm.
Sorry.
Also, I'll just say that it's not a super important function here. You can definitely move on from it. Another option would be print sleep DF. Doing this, well, oh, great, that worked. Another option is to print it, but yeah, I'm glad that viewing it worked. All right. I don't know why. I've always been able to use it without the capitalization.
I don't know. Yeah, I don't know why either. Wonder if it's a version thing.
Yeah, it might be. I'm one like half version behind in R, so maybe that's it.
No problem.
All right. So back to what I was saying about subsetting. So for the subsets, we do sleep DF, and then we select the different column names we want. So if I run this, I am going to get a data frame like this. So you can see we only have the 3 columns we were looking for. And then the other way to subset data is that we can use the subset argument of the subset function combined with a relational operator to grab rows that meet a certain specific criteria. So here once again, I'm subsetting my sleep data frame. And then we set it, then we take subset and we say that we only want feeding behaviors that are equal to carnivore. So we're going to run this. You can see here that we only have carnivores now in this subsetted data set. But wait a second. I mentioned relational operators, but what are those? What does relational operator mean? I imagine some of you aren't familiar with this term. So let's have a side note and discuss this a little bit. Relational operators are small bits of code that return true or false answers, depending on whether or not a certain condition has been met. So as an example, we can ask the computer essentially, does 2 + 2 = 4? And when we run this, we can see down in the console and down here that yes, 2 + 2 is equal to 4. But if we ask it, is 2 + 2 = 5? We get false. Another example is exclamation mark equals, which is not equal to. So we ask it, is 8 not equal to 8? And it says false 8. It says false because yeah, these two things are equal. Then there's greater than or lesser than, where we ask it, is 8 greater than 4? And we get true because yes, 8 is greater than 4. That's pretty simple, but where it gets a little more complicated is when we decide we want to link relational operators together, which we can do in 2 ways. The first way is using the AND symbol. And when we do this, it represents an AND statement. Now, AND statements will only be true if both conditions are met. So for example, I ask it, is 8 equal to 8? And is 8 greater than 4? We run it, and that's true. But when I ask it, is 8 equal to 8? And is 8 greater than 12? It says false, because even though this one is true, we need them both to be true. The other version of linking operators together is using the OR statements, which are specified using this little kind of like straight line thing, which you should be able to find right underneath your delete key. Now, or statements are true as long as at least one condition is met. So as an example, we can do one where both are true, is 8 equal to 8 and is 8, or is 8 greater than 4, and that's true. And then if we do is 8 equal to 8 or is 8 greater than 12, it still comes out as true because at least one of these was true. We just need one of them to be true when we construct these or statements. Right, and with that, let's get back to subsetting. So the way we can do this is that we can filter using multiple parameters using this and symbol. So for example, again, subsetting our sleep data frame, and for the subsets, I'm asking only data where the feeding behavior is carnivore and where the order is cetacea. So we run this and we get a nice little data table like this one, where it's just all of the carnivorous whales. And then using the or symbol, why I find this is the most useful is when you want to choose multiple categories from the same column. So we're going to subset the sleep data frame, and we're going to choose any time that the feeding behavior is carnivore or omnivore. So running this, we can see now that we have a mix of just the carnivores and omnivores, but no herbivores. I also want to mention that you can subset the values in numeric columns as well. This function here will only look at animals that have a body weight above 100 kilograms. So running that and scrolling over, we can see that we only have these really heavy animals now. And finally, to kind of take all of this and put it all together, you can combine the subset and the select arguments to grab rows that meet a certain criteria and then select specific columns at the same time. So I'm going to create a new function, and I'm going to actually save this one. New data frame, and I'm going to save this one. I'm going to call it sleepy herbs. And in this, I am going to subset the sleep data frame, and I'm going to just choose herbivores that get more than 13 hours of sleep a day. And I'm going to look at then just the name, order, and total sleep for these animals. So run this, print sleepy herbs. And we can see here, we now have all of these sleepy herbivores that get way more sleep than I ever have a chance to. And this here is really going to be kind of the basis for this next question we're going to ask. So I'd like you to sort of look at this a lot when we are answering question number 2, because I'm going to ask you to subset our sleep data frame to create a data frame that only includes primates with a brain mass greater than 0.1 kilograms. And when you do this, I also want you to just select the name, the order, and the brain weight columns to stay in your final data frame. I also want you to save this data frame as a variable named smart monkeys. So I am now going to give you around 5 minutes to answer this question. And of course, if you have any problems, please just ask us a question, type something in the chat, and we'll get right to that. All right, I'll start the timer now. All right, time is just about up. So now I'm going to copy in the answer again. And we're going to look at how we do this. All right, so all we are going to do for this is we're going to put smart monkeys and we're going to equal that to subsetting again the sleep data frame, almost exactly like what we did up here. Then we're going to choose order equals primates, brain weight greater than 0.1 kilograms. And we're going to select the name, order, and brain weight columns. We can then print this out. And we should get something that looks just like this. All right, I hope all of you were able to complete that successfully. And now we are going to move on to the last thing we're going to cover in detail with data frames, which is how to analyze and add elements to data frames. So I guess I'll just launch into this. So if we want to calculate something from a data frame, we can actually use these calculations or do these functions directly on the data frame parts themselves. For example, if we wanted to calculate the average total sleep and the standard deviation of total sleep across all of our different species, we can run mean sleep data frame, then money sign sleep total. So this is going to calculate the mean of that entire column. So we run this and we get a mean sleep of about 10.4 hours. Then we can do this again for standard deviation. And we get a standard deviation that's pretty high at about 4.45 hours. So a bit of variance there. And then another thing we can do is we can basically, this was like taking the whole column and calculating something from it, but we can also calculate things from like each individual row. So for example, we're going to calculate how long each species spends awake based on the sleep column. So I'm going to take 24, the number of hours in the day, and minus that by our total sleep. When I do that, looking up in values again, we can see that I now have this big vector that contains all of these awake times for each animal. And we can actually add the awake column to our data set by running sleep df awake equals awake. So now we're using this money sign to define a new column rather than calling to a column that's already there. So I'm going to run this. And then if I just quickly type out view sleep df again, you can see that there's now a new column at the edge of our data frame that is called awake. This is obviously very useful because after you do a bunch of calculations using these columns, you often want to add them on to the original data frame. And once we've done this, we may want to save our altered data frame with this extra information. And we can do this using the write.csv function. So you can see here, we just put write.csv, then the name of the data frame. In these quotation marks, we put the name that we want the file to have. And then for row names, we want to set this to false. If we had set this to true, what we'd get is all of these numbers at the very end would be attached to our data frame, which we usually don't want. So I'm going to run this. All right, and now that I've done that, we can move on to question 3. This is going to be our final data frames question. Well, I want you to calculate the ratio of brain weight to body weight for each animal, and then add that as a new column to our data frame. And then finally, I want you to save that data frame as a CSV file. This one has a couple different parts, but I think they're all pretty easy. So we're going to have this be another 4-minute question. Now I'll set the timer now.
And if anyone has any questions at all, feel free to ask.
All right, time is just about up, so I'm going to go over the answers to this question now. So looking again at the answer sheet, copy and pasting this over. So in order to calculate our weight ratio, all we had to do was look at the body weight column, and we divided that by the sleeping column. And then what we had to do is simply add this as a new column that I named weight ratio. I think I didn't specify it, but you could have named it anything you want, doesn't really matter. And then we saved this as sleep df. I named it this and specified those were false again. So running this, and something I forgot to point out is that you'll actually be able to see this pop up in our little files area after we run this. And then if there aren't any questions about this question, I'm going to move on to our last point about data frames, which is just a brief discussion on how we can combine different data frames together. So in data science, we often find ourselves in situations where we need to combine multiple data frames. Now, doing this is really complex because there's lots of different ways we can do it, so we don't have time to cover it in detail today. However, we still want to describe a little bit about some ways that can be done and when we'd want to combine data frames in these ways. So the first one is R-bind. This is short for row bind. It is the simplest kind of combination. It literally just lets us take a data table and we stack another data table right on top of it. This is for when we have two data tables that have the exact same rows, and this is often useful when working with multiple really similar data sets. For example, maybe you have separate data sets that are each collected for different years or months, and you just want to combine them all together into one. Then the more complicated version of combining data sets, and often more useful, is the joins functions. So join functions merge two tables based on a certain key column that is present in both data tables. For example, you might have two tables that list different information from the same test subjects, and you want to combine all of the data together based on the subject name column. So now you have all the data from both tables that have kind of been merged together into one. That's all we're going to talk about on this today. Joins get very complicated. There are 4 basic kinds, all of which do different things. But if you would like to know more about combining data frames, I would really suggest you see chapter 13.4 of the R for Data Science online textbook. This textbook is totally free and open to all. We also hope to cover this in a later tutorial as well. But now we're going to move on to plotting in R. So let's go through the basics of ggplot. R has some pretty good built-in plotting software, but we're going to be focusing on this ggplot2 package I've mentioned, which is part of Tidyverse. There are a variety of different minor reasons that ggplot2 is superior to R's built-in plotting software, but the main reason we will be using ggplot2 today is because it is much easier to create visually impressive plots using ggplot2. And then at its core, there are 3 main things we need to consider when creating a ggplot. First, we initialize the plot, running ggplot, and this just creates a gray square. It doesn't do anything, really. But then we can start adding stuff to this blank canvas we've created. So we add on our data, and we choose aesthetic mappings for it. Now, for the purposes of today, I just want you to think of aesthetic mappings as how we kind of figure out what our X and Y variables for our plot are going to be. So we just put mapping AES. X is going to be our sleep total column, again, using our sleep data frame. And then Y is going to be our REM sleep. So we're going to do this. And you'll notice that, again, there's no plot really happening, but we have our 2 axes are defined now, sleep REM and sleep total. Now, when we want to actually add something onto these graphs, we need to use a geometric object to tell ggplot what kind of plot to make. So once we have done all of this, we're going to put a plus sign, and then we're going to add on geom_point. And this is going to tell ggplot to create a scatter plot from our x and y variables. So we're going to run this. And I see there's a question. So people who are getting error in ggplot, I would suggest perhaps try and run the library command again. So just go back up to this point and run this. And if this isn't throwing any errors at all, then you should be able to run ggplot. I'm going to take a second to see if that works. And then maybe while I'm waiting to see if that is worked, I'm going to offer one kind of alternative. Let me just scroll back down. If that still isn't working for you, what I would suggest is first typing in, I'll actually send it into the chat, install.packages. Oh, okay, that worked. Did that work for both of you? Awesome, great, that worked for both of you. Okay, I won't say the alternative then because it's not the way we should do this. It's just something else that may have been able to help if something weird was happening. All right, so running ggplot here. I'm just gonna restart this little section again. So when we add this geom_point, it tells them how we should plot our data points. So this aesthetic mapping kind of tells it what the data plots are, and then this is used to define how we're going to show them. Let's look at one other kind of graph before we move on, although we're mostly going to be looking at scatter plots today because they're a simple example. So we can create a box plot that conveys the average brain weight for each feeding habit. So again, running ggplot, all this is the same, and we're going to make our feeding behaviors this categorical variable on our x-axis, and then sleep REM on our y-axis. So running this, we can now see the average REM sleep for each of our feeding behaviors. And this is going to be important on this next question we're going to be covering, as it's going to be require a very similar plot. Okay, and I also want to provide this reference. This includes all the different geom names and the plots they make. So by visiting this website, you can see all of the different geoms you can use, which will tell you how to make different plots like histograms or bar plots, etc. So now we're going to look at adding complexities to our plot, because right now we have this very, very basic, simple looking plot right here, and we want to add some stuff to it. So what we're going to do is we're going to take this plot and we're going to just add on more and more elements to make it more informative. So first of all, we can actually add several plots on top of each other by just adding more geom layers. So we have here our original plot, and then we are going to add on this smoothed plot to it. So I'm going to run this now. This may take a second. And then looking down here, we can see that we've added this nice smooth line. This was created using lowest smoothing, which just creates like a rolling average. And we have added this onto our ggplot. Another thing we can do is change the color of the plots. This is very easy. Just for each of our geoms, we're going to put color equals something, equals red, equals black. We can run this. And now we have a nice black line that's going through our red lines. I prefer this a little bit to the original black and blue. And now we're going to add some titles for our plots and some more informative axes labels. Right now we have these really short ones, but we're going to add a title and some more descriptive labels. So running this is using the, we add on the labs function. And after we've done this, we can see we now have our example graphs and our sleep.
Sorry to interrupt you. Question for you. Question from Derek. Does indication matter in R in grouping commands, or is it done by plus sign?
So the way we do it is in ggplot, the plus sign is the important part. I'm actually curious. I'm not sure if the indentation is even important. Let me try this. So the indentation actually doesn't matter. It is traditional that you put a little space after the plus sign, because that is it just makes it easier to see the first ggplot and what you've added onto it. But the short answer to your question is the plus sign. It's done by the plus sign.
Awesome.
All
Thank you.
right. So I'm going to run this again, and we have our titles now. And at this point, our graph is looking pretty good. And a great thing about ggplot is that we can actually save our graph as a variable, and then we can add more stuff to it later, which makes it easier to not make this whole function too complicated. So I'm going to save this. I'm going to call it our graph. And we are going to actually use this in our next section. Our next section is going to go over how to make our plots more presentable. So the graph we created at the end of the last section, that looked pretty okay, but there are still some things I kind of want to change about it. So looking at it again, I don't like how the title is over there. I don't like these gray boxes. I can still do a bit better. Now, in order to change these things, we will need to alter the themes of the plot. Now, themes are essentially responsible for controlling all the stuff about a plot that has nothing to do with the data or the labels of the plot. They are purely aesthetic. And there are two ways we can alter the theme. We can add a new type of theme that will change the style of the whole graph, or we can alter specific parts of our themes, which does stuff like adjusting the font sizes. Now, there are a few different themes that are built directly into ggplot2, which we will be using today. However, when one considers all of the additional themes that can be made available via additional packages, there are hundreds of themes to choose from. So if you ever have a really specific appearance in mind for a graph, I suggest you look at the additional packages such as GG themes, which there is a link to their website here. And this can give you some more ideas. So now let's really quickly go over this. So we've taken our graph, and I'm just going to add a theme called Classic to it. And now we can see that rather than all those gray boxes, we see something that looks a lot more traditional. Now, another thing we can do is we can adjust the font sizes. So you can see here after theme classic, I'm now putting theme and then the axis title. That's going to be our X and Y axes titles. I'm going to increase the font size to 18. For the plot title, I'm increasing it to 22. And I'm actually, this H adjust means I'm moving the title from over there on the side to the center. And then finally, I'm going to change the axis text, which is actually going to be our numbers along the axis. So running this, we now have some slightly larger fonts along our plot. And then the last thing I'm going to go over is how we can change the type of font that you are using. So this is also pretty easy. Again, you just add theme, text equal element text, and then family equals the name of the font. I'm going to switch this to mono. And now we have this sort of more kind of traditional robotic font. Now, one of the great things about R is that it has an impressive total of 3 whole fonts built into it. Now, if for some reason you require more fonts than this, you will have to utilize the extra fonts package, which also requires you to downgrade another package. I've put the instructions for how to do that here, but because it can be kind of annoying and because you do have to kind of change one little thing by downgrading this package, I'm not going to go over it today. And I'm actually going to take a short break now because I can see that we're just about at the end of our time here. So what we're actually going to do is we're going to go a bit over time. And I hope that some of you are able to stay for that. But if some of you do have to go, we will be uploading this recording so that you can look over the last, I think it's going to be just like 10 or 20 minutes, probably just 10 minutes, not counting the questions. And also, of course, you guys already have all of the content from the GitHub. That being said, before you go, I do want to just bring up one slide that I just want everyone to see. It is these last two slides. Oh, not that one either. There it is. So I want to talk a little bit about this additional information slide. This is at the end of the PDF that all of you got through GitHub. This is going to go over all of the, this is going to give a bunch of different links to pages that can be helpful for learning more. And there's also this last slide, which is a wrap-up slide. This talks a little bit about data binge. This is something that the Dynamic Brain Circuits Research Cluster does. If you have any problems with this tutorial or struggling with something, or really if you're struggling with anything data analysis related, maybe in the projects you're doing right now, I really recommend you reach out to us. This is a link to the Data Binge webpage. If you click on this, it will give you some more information, and then you can reach out to one of us and we'll basically add you to a Slack channel where we have these weekly meetings on Fridays where people come and they get help with their code. And finally, I want to highlight this link for an exit survey. This is basically just a way for you to tell us how we did, tell us any ways we might be able to improve. Please fill out this survey so that we can figure out ways we might be able to improve this format for next time. All right, with that, goodbye to anyone who has to leave right now, and I'm just gonna keep going. Hopefully some people are able to stay and complete the questions, but if not, I hope you'll get to them later. All right, and I'm gonna go back to R now. There we go. All right, wait, couple, oh, thank you. Thank you, you're very welcome. All right, so the last thing we're going to cover with plotting is saving the plots. So once we have created a plot that we are happy with, we are going to want to save it somewhere on our computer. And the best way to do this is to use ggSave because it gives us some helpful options for saving graphs. I just want to take a moment to please recommend that you don't just right-click this and click Save Image. It doesn't work as well as ggSave for reasons I'm about to go over. So just doing a really basic thing, we can just put ggSave and then a name. We don't even need any other outputs. It's automatically going to save the last graph we made. So we'll just run this. And you should see a little mygraphbasic.png appear in our files. I can even take a look at this. And it looks great. Now, a good thing about ggSave is that you can actually alter the plots as you're saving them in some useful ways. For example, you can change the aspect ratios by changing width and height. So I'm just going to create a graph that I call my graph crunch, which is just going to squeeze everything together by making the width and height a lot smaller. So I'm going to run this. I've got crunch. You can see now that we have this crunch down graph. And the reason I did this crunch is because I wanted to point out that even though our graph is smaller, our text is the same size. So you might have to mess around with the font sizes and the graph sizes a little bit to get the plot saved exactly the way you want it to. And one other thing I want to say is that we can, of course, not make these equal. So you can make a very stretched out, a very tall graph, which can be really helpful when trying to put things together into a figure. And then finally, the resolution of our plot can also be adjusted. The default resolution is 300 dpi, but we can increase this. For example, this just creates a 600 dpi plot. And this is really helpful if you are maybe trying to create a poster and you want to balloon out a graph in some way. You can use this to really increase that graph size without, without losing any detail. Okay, so now we're going to move on to question 4, and this is our last major question. I do want to really go through this in case people have some problems with it. But what I'm going to ask is that you create a dot plot with an overlaid violin plot to show the total sleep for animals from a SleepDF data frame with each feeding behavior. This is going to be done using geom jitter and geom violin plot. And once you have created the basic plot, I want you to improve upon it in the following ways by adding all of these extra little bits to it that are going to create a beautiful little plot. And then finally, I want you to save that plot to your computer. This is easily the hardest question I'm going to ask today. It requires you to kind of combine almost all of these sections together. The one hint I'll say is that this basic plot, this jitter plot, as it's called, or a dot plot, is going to be based upon the style of this box plot. So maybe kind of use this style just to kind of get the first bit done. That being said, I'm going to give, let's say, 9 minutes to complete question 4. So I'll be back in 9 minutes. And if anyone has any questions or has any problems with this, please just let us know. All right. I hope everyone was able to complete that slightly more difficult question. I'm going to take a second to quickly go over the answer now. Since we're on overtime, I'm not going to describe it in too much detail, but let's just kind of take a look at what our results are. So running through all of this, creating our violin plots and our jitter plots, adding on all of our titles, adding the theme, adjusting theme stuff, and then finally saving it, you should end up with a graph that looks something like this. There might be a couple little alterations you've made. Maybe you chose different colors, different fonts, etc. That is all very cool. But hopefully you managed to get something around this style. And with that, we're actually going to go into our last short little section today, which is on running a statistical test. Now, surprisingly enough, this is actually going to be maybe the easiest thing we are going to do today, because the t-test function in R basically does all the hard work for us. So the first thing that we're going to do is I'm going to show you how to complete the one sample t-test, and then I'm going to ask you to figure out how to do a two sample t-test. So just as a quick reminder, a one sample t-test is used to test if the mean of our sample is equal to a certain value that we just kind of define. So if we get a p-value below 0.05, then we can reject the null hypothesis that the mean of our data is equal to this value that we maybe found in the literature or we came up with, which was our null hypothesis. Then there is the two sample t-test, and this is quite a bit more popular. This is used to test if the mean of two independent samples are equal to each other. So if we get a p-value below 0.05, then we can reject the null hypothesis that the means of the two samples are equal. Now, rather than using a sleep data frame, I'm actually going, because if we tried to use that, we would end up breaking the assumptions of the t-test. Instead, I'm going to make a couple of samples for us. I'm going to call them sample 1 and sample 2. I'm going to do this with the rnorm command. And basically what this command does is that it just draws some samples from a normal distribution. I'm not going to go into too many details of what that is, but it sort of draws some, not random samples, but a certain set of samples in a way that won't break any assumptions for the t-test. So going to run both of these. And now we can perform the one sample t-test. This is done using a built-in function in R. And we're just going to test if the mean of our sample 1 is equal to 7. Going to run this. And then looking at our output, we have the t-statistic. We have the degrees of freedom. I won't describe what these are in too much detail. Again, maybe something for a later tutorial. And then we have our p-value, which we can see is 3.7 e to so 10 to the negative 6. This is an extremely small p-value, and it's what we'd kind of expect, because I know from looking at this that I set my mean to 10, and I'm asking, okay, is my mean equal to 7? It is not equal to 7, so the t-test was correct in saying that we can reject the null hypothesis that the true mean is equal to 7. And with that, I'm actually just going to leave this question 5 as homework. It's not very hard. It just requires you to perform a two sample t-test on using our sample 1 and sample 2 vectors. You can use the help function to figure out how we can use the t-test function to do the two sample t-tests. It's pretty simple. And just as an extra little thing, I want you to try and specify that the variances are going to be equal for our two samples in this test, as I have set the standard deviations to be equal for both of our samples. And with that, I am going to switch things back to the slides one more time. And I want to take a second to describe this additional information in a tiny bit more detail, just what these all are. First, there is or for data science. Again, this is an online textbook. It's free. It is like the Bible of data science and all. It is, well, I use it all the time. Half of this tutorial was based upon the lessons I've learned from reading it. I highly recommend. I also highly recommend this introductory R tutorial that was made by the Brain Circuits Research Cluster. You can find a link to that here. I suggest looking at the Tidyverse website. This is going to be very helpful when you're just trying to learn more about the different packages in Tidyverse. We looked at ggplot2. There are a lot of other ones that are very useful. Then this is a ggplot2 reference page I talked about before. This has all the different geom names. So this will tell you how you can create all the other kinds of plots you might want to make. This is the R Graph Gallery. This is a very useful website full of well-made tutorials on how to make these beautiful graphs in R. This is really helpful if you have a specific look that you want to get for a graph. One example of some helpful things they have is that this here is a link to a page detailing all of the available colors in R. So this can help you if your basic red, green, black, and blue, if you aren't looking for something like that. And then finally, again, there's GG themes. This is a package that offers more themes than you could ever possibly need. There's even like comedy themes in it. It's very interesting. I suggest just looking through it. And again, if you have a certain look in mind for your plot, you can find a way to get it using GG themes. Then again, I think I summed up this slide fairly well already. Please visit DataBinge if you have any additional questions, either about this workshop or about your own analysis. And please take a minute to fill out our wrap-up survey so that we can know how we did and know how we can improve things for next time. And that's all. I guess thank you all very much for coming, and thank you all of you who were able to stay over time. I will be here for just a few more seconds if anyone has any additional questions, but I think we can stop the sharing now.
Yes, and also thank you, Keegan, for all your hard work and putting this all together. Really appreciate it.
You're very welcome. Thank you.